Okay. So it's time to start, right?
Yes, it just knocked over to 4:35.
Okay. All right. So I think I recognize all of your names. So I assume that you were all here on Tuesday for the previous lecture. So this is the continuation, like the second lecture on radiation detectors and counting statistics. So I will just give you an outline, what we will cover today. So I'm going to build upon what we talked about on Tuesday and go into more details regarding detectors for nuclear imaging and also detector characteristics that are important for nuclear imaging. And really characteristics that are applicable to any radiation detection system. So I'm going to start with detector characteristics. I will do a quick recap of the detector types that we talked about last week, or not last week, but on Tuesday. I'm going to find my, sorry. Trying to find my laser pointer. Okay, there we go. Okay, so I will do a quick recap of the detector types, and then I will talk about specific detectors for SPECT and specific detectors for PET. And I will also talk a little bit about segmentation of scintillators, because that's an area where part of my research is in this area. So to start, as an introduction, so this is an overview of the three main medical imaging modalities that are based on ionizing radiation. So I will focus on nuclear imaging modalities, which is PET, positron emission tomography, and SPECT, single photon emission tomography. So these two modalities are referred to as emission imaging, since in both cases we have a radio tracer that's administered to the patient, and then we measure the radiation that is emitted from this tracer. So in both cases, the radioactivity is emitted from inside the patient, and the goal is that we want to image the distribution of this of the radio tracer within the body to get a functional image, because this distribution is related to different functions in the body depending on what tracer you use. So in PET, the tracer is a positron emitter, which results in the emission of two back-to-back 511 keV annihilation photons that are measured by two opposing detectors, like you see here. So each event is detected by a detector pair. And because they're detected together, we know that the event originated from the line connecting these two detectors. I will go into more details about this when we come to the PET part of the lecture. So in SPECT, we have also the tracer is emitted from inside the patient, but the tracer is a gamma emitter. So in order to find the directionality, we can't use two opposing detectors as we did in PET, but we get the directionality by using collimators so that we know where the radiation came from. And then the third type is computed tomography, CT. So this is, instead of emission tomography, it's transmission tomography, meaning that we have an X-ray source on one side of the body, and then we measure the radiation that's transmitted through the body by using detectors on the other side. So different body tissues will cause more or less attenuation of the X-ray beam that we send through the patient, and that the pattern that we will see on the detector can be used to build up an anatomical image. So CT is anatomical imaging and PET and SPECT is functional imaging. And CT is often used together with PET or SPECT, so that you can overlay the functional image on an anatomical image to make it easier to correlate the region of the tracer. And the CT data can also be used for attenuation correction in the formation of the PET and SPECT image. And I think this is something that will be discussed further in future lectures that are more focused on image reconstruction. Okay, so now that we have an overview of the imaging systems that we're focusing on, so let's go back to the actual radiation detectors, because they are an important, very important part of these systems. So it's good to think about what is it that we want our detector to measure. So in imaging systems like these, there are three main things that are typically important to know. So firstly, we want to know where in the detector did the gamma photon interact. This is important because of spatial resolution in our final image and the quality of our final image, and because the accuracy of this estimation will directly translate to the image, final image. And we also want to know often what was the energy of the photon. And this is important because you want to reject any photons that were scattered within the body before reaching the detector. Because in such scatter events, there are two things that happen. The first is that the direction of the photon will change. So the direction with which the photon enters the detector is it's not directly correlated with the point of emission. So that's why we want to reject the event, because we can't tell anything about the origin of the photon by using it. And the second thing that happens is that the scattered photon will have a lower energy compared to the original photon. And this can be used to differentiate between unscattered events that we want to keep and scattered events that we don't want to keep. And we also want to know in PET when the interaction happened, because we need to determine if two events in the two opposing detectors, if they happened at the same time, and to know if they are connected to the same positron emission. And an ideal imaging detector to achieve all of this would have high spatial resolution, high energy resolution, good timing properties, and high detection efficiency. And it would preferably be cheap as well. And it's very hard to achieve all of these things at the same time. So typically you have to do trade-offs depending on your application. You have to decide what is most important. Is it most important with timing, or is it most important with energy resolution, or where do you want to focus? And then try to optimize the other parameters as best as you can. Okay, so now I will go on and define and talk more about these important detector metrics or characteristics. So to do this, the first thing I want to do is to introduce the concept of the pulse height spectrum. So if we recall from the previous lecture, the two main interaction mechanisms that we have in nuclear imaging is the photoelectric effect and Compton scattering. So for the photoelectric effect, the complete energy of the incident photon is absorbed in the detector. But for Compton scattering, on the other hand, only part of the energy of the photon is lost in the interaction, or it's transferred to a photoelectron, which will then be absorbed in the detector. But part of the energy of the incident photon will go to the scattered photon. And this scattered photon can either be later absorbed in the detector, or it can escape the detector. And if it escapes the detector, only part of the energy of the incident photon will actually be deposited in the detector. And we should also remember that for these type of detectors that we are talking about, the energy of the of the pulse that the detector will generate as a response to these interactions will be proportional to the amount of energy that was deposited in the detector. And this would only be the same as the energy of the incident photon in case all of the energy was actually deposited inside the detector. So if we look at the pulse amplitudes that we would get from our detector for a train of random events, you see on the x-axis here, and on the y-axis we have the pulse amplitude. And we will have a few things, a few cases on what can happen. So if we first look at the smallest signals here, they correspond to events where we have single Compton scattering. So this means that we have the incident photon, Compton scatters, but this scattered photon will escape the detector. So only the energy deposited in this interaction is what we will measure. So this energy can vary, because you see we will have varying pulse height in this region, because the energy of the scattered photon and therefore the energy deposited in the detector will vary depending on the scatter angle that we have here. So it will be different pulse heights, but always lower than the complete energy of the incident photon. So in the second region, we will have slightly higher pulse heights, and this is correspond to multiple Compton scattering, which means that this scattered photon can in itself also scatter and deposit more energy, and then in the next interaction, the scattered photon will escape. So this will be something in between the full energy and the single Compton scattered energy. And then the third region, we have the photoelectric region, which is when the full energy of the incident photon is deposited in the detector. And these all have the same height because, and this height corresponds to the full energy of the incident photon. And this can be either due to the photoelectric effect only or due to Compton scattering plus the photodetector effect. So any event where all of the energy will be deposited in the detector. So from this, we can create a histogram. So in this histogram, we have the pulse amplitude on the x-axis, and then we have the relative number of counts on the y-axis. So we can see that there are, and this spectrum, this is what we refer to as the pulse height spectrum. And we can see some features in this plot. We see here the photopeak, where the full energy of the incident gamma was absorbed in the detector. And then we have the Compton region, which is this one, or the Compton continuum, which is a region with varying pulse amplitude that we saw before, because it depends on what the scattering angle will determine how much energy will actually be deposited in the detector. But we have a pretty sharp cutoff here, which is called the Compton edge. And this corresponds to the maximum energy that can be deposited in the detector from a single Compton scatter. And this energy can be determined from this equation. This is the equation that relates the energy of the scattered photon with the energy of the incident photon and the scatter angle. So if we look at, so this is the energy of the scattered photon. So the energy deposited in the detector will be the energy of the incident photon minus the energy of the scattered photon. So the energy deposited in the detector will be maximized if this expression is minimized. And this will happen when the scatter angle is 180 degrees. So when we have complete backscatter. So we can also see that in this case, this energy will always be there, but even if in this case, when we have complete backscatter, there still will be some energy that is transferred to the scattered photon. Hence the cutoff here, which is at lower energy compared to the photopeak. And we can also see here in between that we have the region for multiple Compton scattering, which is higher compared to this region, and it goes like a bridge between the Compton continuum and the photopeak. So however, what we saw in the previous slide, this spectrum is an ideal spectrum. So in reality, we will get something that looks more like this. We will get a broadening and smoothing of all of the features that we see in this spectrum. So we see the Compton edge is not a sharp edge, it's more like a slope. And we also see that the photopeak is not a sharp spike, it's broadened basically. So this broadening is due to the stochastic nature of the different things that are part of the detector chain. So in the scintillator detector, for example, these random variations can be the statistical variations in the number of optical photons that are generated per keV, meaning that for a given amount of deposited energy, it will not always be exactly the same number of optical photons that will be generated as the response to that energy deposition. And there will also be variations in the number of photoelectrons that are generated per optical photon at the photodetector. And there can be non-uniform sensitivity across the photodetector area, and also non-uniform light collection efficiency across the detector volume, meaning that different number of optical photons will reach the photodetector depending on where in the detector volume the interaction happened. And that is also going to cause differences in the amplitude of the final signal. And so all of these variations will result in the fact that even if all incident photons on the detector will have the same energy and they will all undergo photoelectric absorption, there will still be variations in the signal amplitude that's generated by the detector. And this is manifested as this broadening of the photopeak. So this is very closely related to the energy resolution of the detector. So the energy resolution is the ability of the detector to distinguish two events with different energies. And it's often expressed as the full width half max of the photopeak relative to the height of the photopeak. So you can see here that we can imagine that if we would have, this is a spectrum of cesium-137, which has a 662 keV gamma ray. And this is a very common isotope that's used to compare energy resolution across different detectors, because you need to, when you compare the energy resolution, you will need to compare it for a given photon energy, because it's going to be different depending on the energy of the incoming or the incident photon. So how you determine the energy resolution is that you look at the photopeak and you will see, you can determine what's the width at half of the max of the peak. And then you typically express the full width half max as a percentage when you take the width and you divide it by the maximum height. So in this case, it was the energy resolution was 77% at 662 keV. So it's pretty obvious that you want this peak to be as narrow as possible to be able to distinguish it from another peak that's very close in energy. And for in nuclear imaging, you want a high energy resolution because you want to be able to reject scattered events from scattering within the body, like we talked about before. And when we compare different detector types, semiconductor detectors typically have a better energy resolution compared to scintillators. And for scintillators, the limiting factor in the energy resolution is typically the light yield, which means the number of optical photons that are generated per keV of the incident photon, because the number of optical photons will be the, from a statistics point of view, they are they are the first information carriers that you have. So anything that happens later in the chain will be affected by the number of optical photons that you have. Okay, so second property that I want to talk about is detection efficiency. So we talked about this in the last lecture, that due to counting statistics, the accuracy of our measurement will depend on the number of events that we have in our detector. And because of this, it's very important that we have high detection efficiency. And we typically talk about two types of detection efficiency. We have the intrinsic efficiency, which is the number of pulses recorded by a system divided by the number of radiation quanta, or in this case, gamma rays, that are incident on the detector. So the intrinsic efficiency will depend on the material that you use. So it's determined by the detector thickness and the stopping power of the material in use. And then we have the absolute efficiency, which is the number of pulses that we record divided by the number of radiation quanta emitted by the source. So this efficiency is determined both by the intrinsic efficiency of our detector and also of the overall system geometry. So we can imagine that if we have a point source and we have a very small detector, we will have a very low geometric efficiency. But if we have a point source which is completely surrounded by detectors, we will have a much higher geometric system geometry. And we know that, we already said that a large number of events will yield more accurate measurements. And since we know that this can be achieved by three main ways: increasing dose, increasing measurement time, or increasing detection efficiency. And increasing detection efficiency is the only one of these that can be done without expense of the patient, because both increased dose and increased measurement time will cause discomfort and potential health issues for the patient. Okay, so another concept that's related to detection efficiency is the photo fraction. So if we have a system that does energy selective counting, meaning that we only want to use events in the photo peak, for example, like we want to do in these applications that we are talking about here. If we only want to use the photo peak events, it's very important that we have both high efficiency or high intrinsic detection efficiency, but we also need that as large fraction as possible of the interactions in the detector is due to photoelectric absorption, so that the full energy is deposited in the detector. Because if we have a high detection efficiency, but it's only single quantum scatter that occurs, then it's not much use, because we can't reject scattered events that are scattered in the body. So this photo fraction is basically the fraction of all interactions that is photoelectric absorption. So the photo diffraction depends on the detector material that you use, and it is a function of gamma energy and the detector size. So if you remember from last week, we know that the probability for a given material, the probability of photoelectric absorption will decrease with increasing gamma ray energy. So we see this here in these curves. And the detector size can be used to somewhat compensate for this, because if we have a larger detector, we increase the probability that a photon that is quantum scattered will undergo photoelectric absorption before escaping the detector. And if that happens, we would still have the full energy deposited in the detector, and the event will end up in the photo peak. So these three curves are just different sizes of the crystal that we use. So we see that here for the 5x5 crystal, we will have the lowest photo fraction, and then it increases as we increase the detector size. And this is just an example for sodium iodide, one scintillator crystal. Okay, and then we have another concept, which is dead time. So the dead time is the minimum amount of time that needs to separate two events for them to be recorded as two separate events. And the limiting factors here is both the detection physics, like what we know, for example, that for scintillators we have a decay time, which will cause a broadening, like our pulse will not be instantaneous. It would be distributed in time and it will have a certain width. And this width will determine our, affect our dead time. And we can also have additional delays in electronics that will increase this dead time. So there's always a chance that because we don't have events that occur within, like with 2 seconds separation, and because it's stochastic, and the radioactive decay is stochastic, so there's always a chance that a true event will happen very close to the previous event within this dead time and then be lost. So you typically talk about two dead time models, which are idealized models, and a real counting system will often resemble one of these two the most. So if we look at this, we have the parallelizable model and the non-parallelizable model. So in the middle here, we see events in our detector. So we have 6 events. And for the parallelized response, we see that for the first event, this is the time when the detector will be dead. So this is the dead time tau. And then after this time has passed, the detector will be live again and ready for a second event. But if an event happened within the dead time of a previous event, in the parallelizable model, this will cause this event will not be counted as a new event, but it will extend the dead time of the original event. So we see here that for 1, 2, 3, 4, 5, 6 events, we will only register 3 events with the parallelizable model. So the other model is the non-parallelizable model. And here, what happens when an event happens during the dead time of a previous event, nothing will happen. So we have this event, and then we have the second event, and this one occurs within this dead time, but nothing happens. It's not registered, and it doesn't increase this dead time. The detector is just that it's just lost. So in this case, for 6 events, we will only record 4 of them. So we see that there is a difference in the behavior between these two models. So as I said, a real system will often have a behavior between these two. And the detailed response of a specific counting system will depend on the physics that goes on in the detector itself, and also on the delays introduced by pulse processing and electronics. So this graph shows the measured or the observed count rate as a function of the true count rate for the two models, so the parallelizable model and the non-parallelizable model. And this is the behavior that we want when we have no dead time losses. So the observed count rate is always the same as the true count rate, which is what we want. So we see here that for low true count rates, the two models are very similar, but for higher count rates, there's a big difference. For the non-parallelizable model, we will go asymptotically towards a maximum count rate, which is given by 1 over tau, where tau is the dead time of one single event. But for the parallelizable model, we will reach a maximum count rate at some intermediate true count rate, which is given by 1 over e tau. And then if we increase this would be like a threshold. If we increase this threshold, when increasing the true count rate, the system is so parallelized, so the observed count rate will go down with increased true count rate. So we can see here that for high count rates, the dead time losses of our system can be really significant, really severe, which will essentially cause a loss in efficiency. Okay. So then we have something that's not necessarily a characteristic that is important for all radiation detection systems, but it's important for radiation detection, imaging radiation detection systems. So that is the spatial resolution. So we talk about the intrinsic spatial resolution, which is the ability of the detector to distinguish two events that are taking place close to each other inside the detector. So this is the accuracy of determining the interaction position in the detector. This is typically determined by the detector size and the photodetector size if we're using scintillators. And for the systems that we will discuss today, we can also talk about the system spatial resolution that also takes into account other components of our imaging system. So we'll talk more about this in future slides. So, but for SPECT, we will have also the colorimeter resolution. For PET, we will have the positron range and annihilation photon non-collinearity. But I will discuss more later what this means. Okay, so now comes a little bit of a recap from last week regarding different detector types. Does anyone have any questions so far? No? No questions. Okay, if you have questions during the lecture, you can feel free to just interrupt. Okay, so let's move to the next. Okay, so this is what we had from last week. We have two main types, detector types. We have the direct conversion and the indirect conversion. And in direct conversion, we have semiconductors. I'm not going to talk about the gas-based detectors here because they're not really applicable to imaging because of their low stopping power. So in direct conversion, we have the gamma ray interact with the detector material. And as a response to this, we will get electron hole pair production. And then we can apply a bias voltage across the detector's cathode and anode contacts, and then collect these electrons and holes and generate an electric signal. And then in the second type, which is the scintillation detectors, we have indirect conversion. So we have the same thing. Gamma ray interacts with the detector material. We get electron hole pair production. And from this, we get excitation and emission of luminescence centers, which means that we will have a large number of scintillation photons that are generated. So instead of collecting these electron hole pairs, we will collect the optical photons that are generated as a response to this. So a scintillator is coupled to a photodetector that will measure these optical photons and convert the signal from an optical signal to an electrical signal that we can better analyze. So first, some characteristics of semiconductor detectors. Silicon and germanium are the most famous and common ones. They have pretty small stopping power compared to scintillators, as you can see. So this plot shows the transmission of the material as a function of the detector thickness. And we have here, we can see, yeah, I didn't include silicon and germanium. So we can go on to cadmium telluride and cadmium zinc telluride, which have higher effective C. So remember that these will have higher stopping power compared to these ones. So we can see a CCT here in purple, and then compared to a number of, these are all scintillator detectors. So we see here that for, so if the transmission is 10%, meaning that 90% is stopped within the detector material. For LSO, for example, we only need about a little bit more than 2 millimeter to achieve this. But to achieve the same detection efficiency for cadmium zinc telluride, CCT, we would need almost 7 millimeters. So you can see that that is a drawback of the semiconductor detectors, that we need a lot more detector material. And we also know that they are very expensive to fabricate and hard to make in large sizes. So these two types are the ones that are explored for nuclear imaging applications. Silicon and germanium that have even lower stopping powers are not really interesting for these applications. They're good for lower energy X-rays or gamma rays. One problem is that they also require cooling because to reduce the thermally induced noise. That is a problem in these detectors. But yeah, a few spec systems use CCT. So there are systems that use semiconductor detectors, but not for PET because they have much higher gamma energies that you want to measure. But the main advantage of semiconductors is high energy resolution if you compare them to scintillators. So if we move to scintillators, there are some important characteristics that we need to think about when we choose a scintillator for an application. So we want to look at the intrinsic spatial resolution, like we talked about it before. And here it's important with the detector size and the photodetector size. And also detection efficiency is determined here by density and effective C. So if we have a thicker material, we would have larger stopping power and higher detection efficiency. And we also mentioned this, that for good energy resolution, we need a large light output, meaning a large number of optical photons generated for a given gamma energy. And to have good count rate performance, meaning small dead time, and also good timing resolution. I will talk more about why this is important later. For these properties, we need to have fast decay time, meaning that the emission of the optical photons happen with a short delay from the gamma interaction, from the time of gamma interaction. So here I just wanted to show a chart of time chart of the development of new scintillators. You can see this is a very active field, especially in the past years. This ends 2009, so things continue to happen after here. So people are constantly trying to find new, better materials with better characteristics that can be used for improved detection systems. So medical imaging and high energy physics are the fields that have been driving this development. There's a lot of overlap between research for scintillators for medical imaging and for high energy physics. Another big area where scintillators are used is nuclear security. Okay, so now let's move to the real applications. So we're going to start with SPECT detectors. So this just shows the concept of the basic. Sorry, I just need to throw my daughter out. 1 second. Yeah. Let's go. I don't know where he is. Okay, sorry about that. Now the door is locked, so we should be able to continue. Okay, so this is the basic concept of the gamma camera. So it consists of, we see here a sodium iodide scintillator crystal that's coupled to an array of photomultiplier tubes. And we have the patient here with some distribution of radioactivity inside the patient. So as we talked about, we need a collimator in the SPECT system so that we can determine the direction that the origin of the gamma ray. So the collimators are made of high density materials that will absorb any gammas that are incident on the detector with an angle not aligned with the collimator. So in this figure, we see a parallel hole collimator. So only gammas that enter perpendicular to the detector face will be allowed to enter the detector. All gammas that enter from oblique angles will be absorbed in the collimator and will not reach the crystal. So by doing this, the interaction location in the detector is directly correlated with the emission point inside the patient. So by doing this with a large number of projections, we can form an image of this distribution of radioactivity inside the patient. So in the basic all-purpose SPECT system is a dual head gamma camera, which would be two of these type of detectors that are rotated around the patient to get a large number of projections. And there also exist specialized cameras that focus on certain parts of the body, for example, on the heart. I will talk a little bit more about this later. And the purpose of the light guide that is used here is to spread. We see here that an event happened here, the scintillation light will spread. We want it to spread to reach several photodetector elements so that we can determine the position of the interaction. Yeah, I will talk about this more in later slide. So this is just a picture of what the classic angular camera or gamma camera looks like. So we have here is the crystal, and here are the photomultiplier tubes. So this is a pretty old system. We see that the photomultiplier tubes are quite bulky. Silicon photomultipliers have much smaller form factor, and they can allow for more compact systems that are used nowadays or in development nowadays. So this is how events are positioned inside the gamma camera. So we have our scintillator crystal, and we have our collimator, and we have our photodetector. So this is an array of photomultiplier tubes in this case. So this event positioning method is called angular logic or center of gravity. And it's based on the fact that the photomultiplier tube or the photodetector elements that's closest to the interaction location will receive a higher signal compared to another one that's located further from the interaction location, simply because more light, if this is the cone of light that goes out from the interaction location, we'll see that more light will hit this detector compared to this detector. So the signal here will be higher compared to here. And by doing this in 2 dimensions, you can obtain the XY coordinates inside the detector. And this is important because it's important to determine this accurately, because it will be directly translated to the origin, the accuracy with which you can determine the origin of the gamma source in the body. In addition to this simple angular logic, this is the simplest event positioning algorithm that is used in the majority of the systems, both for SPECT and PET. But there are also more sophisticated statistical methods that can give better intrinsic spatial resolution, especially close to the detector edge, where this method will have some problems. The drawback of these statistical methods is that they require a lot of detector calibrations to be performed for each detector model. Because basically what you do is that you use a source to get events in each location in the detector, and then you see what response you get as a function of interaction location. And then for an event that you don't know where it occurred, you have to compare the signal pattern that you get. You compare it to all of those known signal patterns, and then you can, in that way, estimate where the event took place. So it's more computationally heavy, and also it requires calibration. So in SPECT, the spatial resolution will depend on the intrinsic detector resolution, which includes the event positioning, and also on the collimator resolution. And it's usually dominated by the collimator resolution. And this is how you can add the two contributions to spatial resolution. So the system resolution is just the square root of the squared contributions of each of these components. So the system resolution is always larger compared to the individual intrinsic resolution and collimator resolution. So here I show the parallel hole collimator, which is the most common type. And you can see here the line spread function, which is this one, which is the projection that you get as a response to, if you have a line source on one side of the collimator, and then you see which gammas can come through the collimator, and you can see the distribution on this side. So we see here that one important characteristic of this type of collimator is that the resolution depends on the source to collimator distance, so this distance. So we see here that if we have our source far from the collimator, just the solid angle will result in that gammas will be allowed to come through more collimator holes, which will lead to a broader line spread function, as opposed to if you have the source close to the collimator, all of these gammas will be cut off due to the angle, and we will get a narrower line spread function. So for good collimator resolution, we want this to be as narrow as possible, because that's how it's going to be best correlated with the source location. And there are a number of different collimator configurations that can be used depending on the application and the overall scanner geometry. So here I show 4 different types. And we have pinhole collimators, where we have, it's just a simple pinhole, that's the only opening. So what happens here is we have our object that we want to image, and we will get, with this collimator, we will get an inverted image on the detector plane, which can either be a magnification or a minification of the object, depending on the focal length and the distance, the collimator to the pinhole to object distance. So if we use this in a magnifying configuration, this can be very good for high resolution applications. The downside is that we get very low detection efficiency with this configuration, because a lot of the majority of the gammas will actually be rejected. And then we have the parallel hole one that we saw before, which is the most common one. And there can also be converging or diverging collimators. This one will be minifying, and this is magnifying. And here we can see the resolution and efficiency characteristics of each of these collimator types. And this is as a function of the source to collimator distance. See here. So here we have the resolution, and here I had the geometric efficiency. So we can see that we will all have, in all of these cases, we will have a degradation in the resolution with distance from the collimator to source distance. And we can see the different characteristics of the different types. We can see here, for example, the pinhole, we will have good resolution, but the efficiency is the worst among these first ones. So many times a SPECT system can have interchangeable collimators. So for a certain exam, you may need high resolution. It may be more important than high sensitivity, and vice versa. So you can change depending on what it is that you want to do. You can also use different collimators for different gamma energies, because if you have a lower energy, you will need a thinner septa of your collimator to stop the gammas that enters from the wrong angle. Okay, so now let's move to PET detectors. Is it the time? Okay, So this is the basic working principle of PET. So you have an event happening here. So a positron is emitted. This will quickly annihilate and result in the emission of 2 back-to-back annihilation photons, or 511 keV gammas, that are hitting a detector here and a detector here. So if we measure a signal in one detector and also in another detector, if this signal is measured within a very small time frame, we say that these are coincident events and they correspond to the same positron decay. So we record these coincidence pairs, and then we know that the event took place along the line connecting these two detectors. So for PET, we don't need a collimator to know the direction that the gamma came from, but we use this type of electronic collimation instead of the physical collimation that we used in SPECT. Another difference compared to SPECT is that stopping power is more important because we have higher energy gammas that we want to measure. So this is just an example of how a PET system is built up. You can see that we have many small detectors that are coupled to photodetectors. You can group them into modules and then you assemble them into a ring. So you can see here how it quickly sums up to a large number of electronic channels because you have a large number of photodetectors and also a lot of detector material. And this is also why PET is more expensive compared to PET, because you need this full ring to be able to collect all of the lines of responses. And for SPECT, you can have just 2 panels rotating, or 1 panel rotating around the patient. So you need a lot more detector material and not more electronics, which will make a more expensive system. And this is just one example of a PET scanner, just to give you some numbers. In this scanner, we would have 28,388 crystals and 520 photomultiplier tubes. Yeah, so you see that it is a lot. So in PET, we have some other contributions to the system spatial resolution. So we know that the source position can be determined from the line. We know that it will lie on the line of response connecting the 2 detectors that measure the events. So this just illustrates that the detector size is very important here, because if we have bigger detectors, this line of response will be very wide. If we have smaller detectors, it can be thinner. So it will directly affect the spatial resolution that we have. A second component is the positron range. So the positron, when it's emitted from the tracer, it has some energy. So it will travel some distance before it annihilates and emits the 2 back-to-back gammas, which means that there is a difference between the location of the radio tracer and the emission point of the gamma rays, which will cause some uncertainty in the spatial resolution. So for F18, for example, which is the most common isotope used in PET, the maximum energy is 635 keV. And the extrapolated range for this energy in water is 2 millimeter. But the full width half max of the distribution profiles is 0.1 millimeter. So this can be just to show you how big of a contribution this is. Another thing is the non-collinearity of an annihilation photons, which is because we say that these gammas are emitted back to back with 180 degrees difference, but it's not exactly 180 degrees different. There is some deviation. And this will be mostly a problem in large bore scanners, because the difference in this angle will cause a more pronounced difference, especially when you have larger distances to travel. And again, we can obtain the system resolution just by adding the square root of the squared resolution of the individual contributions. So one thing that's also important that we didn't talk about in SPECT, it can be a problem also in SPECT. I will come back to that later, but it is definitely a problem in PET is the depth of interaction, or DOI. And this is, so if we have a ring containing a lot of thin, small detector elements in a ring, if we say that this type of detector will only give us information about in which detector element did the event take place. But if we don't know at what depth within the detector it took place, we will have some problems, because if we then map all of the events to the center of the detector, for example, we will have a nice thin line of response here in the center of the field of view. But if we move towards the edge, if we don't know where along this depth the interaction took place, the line of response would be very broad, and this would translate to blurring at the edge of the field of view. So we will have better spatial resolution in the center of the field of view compared to at the edge. So because of this, a lot of research is being done to develop detectors where we can know the depth of interaction. So if we know along the point along the depth where the interaction took place, we can get a uniform spatial resolution across the field of view. So we get the same width of the line of response, regardless of if we are in the center of the field of view or at the edge of the field of view. And this is a problem mainly, it's more of a problem in small bore scanners, and when we have, because if the bore is small, we will have a higher probability of oblique angles of incidence on the detector face, which is when we will typically have the situation where we will, the gamma will enter one crystal, go through that completely because it enters at an oblique angle, and then interact in another detector element further along. And it's also a big problem in scanners where we have long crystals, long and thin crystals. That's when the most problem is. So there are a lot of approaches to develop detectors to correct for this blurring. Because you can see that one way would be to just use thin crystals, but then we would get a loss in efficiency and sensitivity. So we want to have thick detectors, but we want to know the point and the interaction depth within the detector. And here are some approaches that are explored. Here we see layer detectors. We would stack, instead of having one detector with a photodetector and very long crystals, we stack two detectors with shorter crystals and their own photodetector. So now we would know if it interacted here or here, which will improve our image quality, but we have a more complex detector with more readout channels because we need a double set of photodetectors. Another way is to have photodetectors on both sides of the crystal array. In this way, the difference in signal between these two will be correlated with the interaction depth along the crystal here. Another way of doing it is to use a single photodetector, but have two crystal arrays with different timing characteristics. Where, for example, this array will have a very short signal, and then this array will have a long signal. So if we analyze the pulse shape, we can determine if the event took place here or if it took place here. You can also use monolithic crystals without having any segmentation. In this case, the light distribution on the photodetector here will depend on the interaction depth. If you have interaction very close to the photodetector, most of the light will be confined very close in your photodetector, very close in transversal locations. If you go further here, it would be spread more evenly across the whole photodetector. So the drawbacks of this is that you would have worse transversal spatial resolution, especially if you want to have thick crystals for high efficiency. And then there are also other, like here you have offset detector crystals that would give different signal patterns on your photodetector array depending on the depth. Or you can have different shapes of your pixels in the top and bottom. There are many different approaches that are being explored. And it all comes down to high performance, but having relatively straightforward implementation. And practicality is also an issue. So in addition to depth of interaction, time of flight is another thing. So that's a way of improving the image quality, to use the time of flight information. So this is based on measuring the time difference in arrival of the two photons. So we say that they arrive simultaneously, but it can be, if the event took place closer to this detector, that gamma will reach this detector before this gamma reaches that detector. So if we can measure the time difference between these two events, we can estimate where along this line of response the event took place. So instead of with conventional PET, where we just know that it happened somewhere along this line, with time of flight PET, we can say that it happened within this region. So this, what will happen is that the signal to noise ratio will increase in this case, which will be effectively, we will increase the system efficiency or system sensitivity. So you can get a better image quality, or you can get shorter imaging time, which both can be very beneficial. So we can see here that this is just the basic correlation, that delta X would be the distance from the midpoint between these two. The distance where the event is estimated to originate, the offset from the center point is correlated to the difference in detection time. And to do this, you need fast detectors, because the faster detectors you have, the better you can estimate this position, and the smaller this region will be, which will be beneficial for image quality. So because of this, timing resolution is an important concept in time of flight PET, because the accuracy of the delta X, meaning the position along the line of response, will depend on the accuracy of the delta T, the difference in timing. And to be able to calculate this value accurately, you need good timing resolution, meaning that you need to be able to, with good precision, determine the interaction timestamps in each of the detectors. And there are several factors that are contributing to timing resolution in a scintillator-based PET detector. So this figure just, I wanted to just highlight some of the things that will cause a time jitter, or like an uncertainty in your timestamp that you obtain. So if the total time jitter, it will be a function of the conversion depth, meaning how far do the gamma travel into the crystal before interaction happens. We will also have the scintillation process itself, meaning the scintillation decay. There is an uncertainty in when the optical photons will be emitted from the interaction location. We also have jitter in the transit time, meaning that different optical photons will have different travel length before they reach the photodetector. So for example, we see here, one photon goes straight here, very short time. Another can go and be reflected multiple times within the detector before reaching the photodetector. So this would be a much longer travel time. And there can also be variations in the response time of the photodetector. And then in addition to this, we would have random losses of some optical photons, like some can be absorbed within the crystal. We have a quantum efficiency of our photodetector, meaning that some photons will not be converted to photoelectrons, but will be lost in this interface. And there's also a time spread in the conversion time in the electronics. So all of these will contribute to time resolution. And this is a very hot topic in research, to try to achieve detectors with better and better timing resolution, because it's going to translate to better spatial resolution and better image quality in your final PET image. And you would need to do optimization in all of these steps for the best performance. Another hot area is PET-MR, which is to combine positron emission tomography with magnetic resonance imaging. I already mentioned that you often use PET together with CT to have both the functional image and the anatomical image. It can often be very interesting to do it instead of CT, you want to do magnetic resonance imaging. One advantage of this is that you don't, magnetic resonance imaging, you won't give any additional dose to the patient, so you can do dose reduction with this. And the major difference from a detector design point of view is that for an MR compatible PET system, you can't use photomultiplier tubes. You need to use silicon photomultipliers because photomultiplier tubes are very sensitive to magnetic fields, so they will not function properly. Another thing, given that you use a lot of detector material in PET, system cost is something that is an important factor. If you use pixelated detector, around half of the price of a PET system would be due to the detector material. Or the detector itself. So you need to be able to reduce the price. A lot of efforts are being done to find ways to reduce the number of photodetector channels. So you want to still be able to accurately estimate the interaction location in the detector, but use fewer electronic channels. Also, you can reduce the number of detector rings, which would reduce your coverage. You can use partially populated rings to reduce the number of detectors that you need. Cheaper crystal growth is also interesting to try to increase the production yield, finding new sources for raw material, or use ceramic scintillators instead of crystal scintillators. And also cheaper detector fabrication techniques are interesting. So finally, I will just briefly talk about scintillator segmentation, because as we saw, it's also anything that we can do to reduce the cost here is good. And we know that we want, in order to have high sensitivity and high spatial resolution, we want to have structured scintillators, meaning instead of just one big slab of scintillator material, we want to have something that confines the light so that we can increase the spatial resolution without sacrificing sensitivity. And the problem for many nuclear imaging modalities is that if you want, especially if you want very high spatial resolution, you want very small pixels. There is a problem with the industry standard, which is mechanical pixelation, where you take a big crystal and you cut it into many small pixels and you assemble them with reflectors. And this is not practical. It can be expensive if you want to go to smaller pixel size. You will have material yield issues, high manufacturing costs, and also pixel size variations, so uniformity issues. So one thing that we are working with in my lab is laser-induced optical barriers, which is an alternative technique that can be used to confine light in scintillators. So with this technique, we use high-powered pulsed laser that we focused inside the scintillator crystal, and that can cause a local modification of the crystal structure and the refractive index, which would be, we call these optical barriers that can then redirect the scintillation light and work similarly to reflectors. And this is just a picture of our setup that we have in our lab with the laser and delivery optics and the stage that holds the sample that we can program to draw any pattern that we want inside the crystal. So this can be a very cost-effective and flexible alternative to mechanical pixelation. And this slide just shows that we can do this for a lot of different crystals. it's very material dependent technique, so we would need to optimize the procedure for any material. But you can see here that we can do pixelated arrays that can be used as an alternative to having mechanically pixelated arrays. So one application I just wanted to briefly mention that we are working on right now is we are developing a cardiac dedicated SPECT system that consists of a body contouring geometry. So we have a lot of detectors around the body contour, and we pack these detectors very close to the patients so that we can get a large number of view angles and large detector coverage with high geometric sensitivity without using too much detector material. So this would allow for stationary imaging at low dose and or fast imaging time. So each of these detectors contain a scintillator and a pinhole collimator. And in order for us to go close to the detector or close to the body and to pack more detector models and increase geometric sensitivity, we have this in a minifying geometry. And yeah, I should also say that each of these views the entire heart. So one challenge with designing a detector for this system is to achieve high intrinsic detector resolution in a cost-effective manner. Because we have it in a minifying geometry, we need very high resolution in the detector to be able to compensate for this minification and still achieve high spatial resolution in our image. Another problem with pinhole collimators is that we get DOI blurring. Similarly to in PET, we can get blurring at the edge of the field of view if we would have normal straight pixels. So the solution to both of these problems can be our laser-induced optical barrier technique, because we can make small pixels with high material yield and minimal labor cost. And we can use scintillators, which is more cost-effective compared to semiconductors, which are often used in other cardiac dedicated systems. And another thing we can do is make converging pixel elements that have the same angle. An angle is correlated with the angle of the acceptance angle of the pinhole collimator. So this will eliminate the DOI blurring. This would be very hard to do by cutting the crystal, but with the laser technique, it's a straightforward thing to do. So here just wanted to show some crystals that we fabricated where you can see these focused pixels inside the crystal. And that was all that I had for today. So I'm very happy to take any questions that you may have. No questions?